All right, welcome to, this is going to be day 2 of your notes, which corresponds to page 7 to 9 in your packet. This is kind of an unplanned thing. Our projector died today, so trying to get you these notes through a recording from the document camera. I intend to probably do these a little bit more regularly later in the year. To just have as like an extra resource that you can go to if you miss a lesson or you're absent for the day or whatever. So let's go ahead and try to get into this on going to be page 7 in your packet. So let me go ahead and load the presentation. And we'll get started in a moment. All right, so top of page 7 talks about kinetic theory. We mentioned this the other day, but all matter, okay, atoms and molecules, are always in constant motion due to the energy that they possess. Now, you should know that heat travels from a hotter object to a colder object. So if you think about the flames in the image behind the slide on the PowerPoint here, if you had to describe the direction of heat flow, you would say that heat travels from the flames to the surrounding air, right? Because you know the flames are at a higher temperature than the air, so you know the direction of heat flow has to be from the flames to the surrounding environment or the air around the flames. All right. Well, if you think about what happens when you form ice in the freezer, okay, now freezers are pretty much automatic for most people now, but back in the day you had to actually take a tray, put water in it, and then stick it into the freezer to make ice cubes. So what was going on with heat flow there? All right. Well, if you compare the temperature of the water in the ice cube tray and the air inside the freezer, you would find that the water is actually at a much higher temperature. Even though it's room temperature, it's at a much higher temperature than the air in the freezer. So the direction of heat flow is actually from the liquid water into the air in the freezer. A lot of people would incorrectly say that heat's flowing, or that cold rather, is flowing from the air in the freezer into the water. There's no such thing as cold flow. There's no such thing as cold. Cold is simply the absence of heat. So in reality, what happens is heat leaves the liquid water, goes into the air in the freezer, right? And that's your freezer's job, is essentially to just remove heat from whatever is inside until that substance is frozen. All right. So there's 3 different ways that heat can actually be transferred from one location to another. So we're just going to briefly review these methods. You probably should have learned them in middle school. But the first is radiation. So this is when energy actually transfers through empty space directly. It transfers in the form of electromagnetic waves. And typically heat waves are referred to as infrared waves. And again, this is the only way that heat can actually travel through empty space. So through an area where there are no particles. So for example, the sun is like 92 million miles from the Earth, and obviously we get all of our energy ultimately on the Earth comes from the sun. The only way it can reach the Earth is through the mechanism of radiation. So if you're laying here like this kind of silly cartoon of this guy on the beach, right, and you feel your body warming up as you're in sunlight, then that is energy that's being transferred to you directly by radiation. Second method is called conduction. All right, conduction is what occurs when heat transfers from particle to particle. So this is when heat transfers. Typically, we think of this like with solids, like when heat transfers from one solid to another solid. So if you look at the little picture down here, you can see we have this pan that's on, or a pot that's on a kettle or on a hot plate on your stove. And what's occurring there is whatever heat element, could be an electric element or it could be a flame, is heating up your top of your stove, right? The molecules and atoms in that heating element are going to be vibrating faster and faster, because we said that temperature is really just the motion of particles. So as those particles vibrate and move around, zoom around faster and faster, they're going to come into contact with other atoms that are touching them, right? So in this case, it would be atoms that are on the pan. And so as the atoms down here that are in the stove hit the atoms that are in the pan with higher and higher energy, then those atoms in the pan are also going to start to vibrate and move around faster as they absorb some of that energy through those impacts and collisions. All right? And eventually that heat is going to spread throughout this metal pot as the atoms simply speed up and hit each other faster and faster. All right? So heat transfers from solid to solid or through a solid by the mechanism of conduction, and that is, again, particle-to-particle contact, right? The faster the particles move, the faster they hit their neighbors, the faster those particles start to move and hit their neighbors, sort of like a chain reaction. The third mechanism for energy transfer is by convection, and this is the transfer of heat by actual movement of the warmed matter itself. Let me move this a little bit so that you can actually see it on the screen. But this is how heat spreads through liquids and gases. All right, liquids and gases are not very efficient at conduction, which we just talked about, because their particles are a little bit further apart and they don't collide as often, especially in gases. They're very far apart. But yet, you know from everyday experience that heat can actually travel through a liquid or through a gas very quickly. Right? If you light a fire in a fireplace, or if you have like the heat in your house comes on, it warms up all of the air in your house pretty quickly. And yet it's not through conduction, it's through the process of convection. So the way convection works is there's some heat source in the liquid or in the gas. So in this example, we're talking about the water in the pot. Not the pot itself, which heats by conduction, but the water inside the pot. How does heat spread so quickly so that that water could be raised from room temperature to like boiling temperature within a matter of maybe a few minutes? So how does that occur? Well, before the heat's applied, all the water in there, let's say, is at room temperature. That's like 70 degrees Fahrenheit. Okay. Well, when the heat's turned on, we know the pan gets hot by conduction. All right, so the bottom of the pan, the atoms are moving very, very quickly, and they're going to transfer their heat to what part of the water? Well, it's going to be the water that's obviously at the bottom, duh. Okay, but that water, when it gets hot, it tends to rise. Everybody, also, I think, always heard the phrase warm air rises and warm water rises too. It's got more energy, so that hotter water molecules tend to move upwards. Right? This is the same thing that happens in the atmosphere, by the way, that when moisture forms on the ground, it evaporates and it rises in the atmosphere. It's responsible for a lot of weather. But anyway, back to our pan right here. The water at the bottom gets hot, it goes up, right? And what that does is it actually forces the cold water at the top to sink down to the bottom. So you can see you have this cycle of warm water rising and cold water sinking. Well, when that cold water sinks, it's coming into contact with the heat source that's at the bottom of the pan. So that water that was cold, that sunk down to the bottom, is actually becoming hot too. So then it rises and forces yet more cold water to come down. And pretty quickly, this cycle causes all the water throughout the pan to circulate and therefore get hot. Okay? Same thing is true if you have air in a room and you have like a little space heater in the corner of the room. That space heater causes the air in the room to get hot, to rise. The cold air sinks from the ceiling, moves by the space heater, heats up, rises again, and you have the same thing called the convection cycle. All right, so anyway, let's move on to heat versus temperature. So you need to know the difference between these things. Heat is simply the total amount of thermal energy in a substance. So if I were to add up, if I could somehow figure out how fast all of the atoms in a substance were moving, and I could figure out all of their energy and add all of it up, then that number, that amount of energy I came up with, that's what we would call the heat or the thermal energy in that sample of matter. All right, and we measure that number, that amount of energy in the unit of joules. All right, now that's not like jewelry from a jewelry store, necklaces and whatnot. That's just, it's named after a scientist, James Joule, who was very important in the study of energy. All right, and in the non-metric system, we use the unit calories. There's little calories, and then there's big calories with a capital C. 1 little calorie is equivalent to 1,000 big C calories, if you're wondering what the difference is between those. And we'll actually use both of these units, calories and joules, throughout the year, depending on what unit we're in. And we can't really directly measure the amount of heat in a substance. The only way we can really measure that is by transferring that energy to something else. So for example, if I have like a piece of really hot metal, there's no direct way I can measure the heat in it, but I could drop it into a cup of water and I could figure out how much that water warms up, and then I can infer, based on how hot the water got, how much energy was absorbed from the metal. That's what we mean by indirectly measuring heat. For temperature, the definition is a measure of the average kinetic energy of a substance. So temperature is really only concerned with the average speed of the molecules in a sample. But notice there's nothing here about mass, right? So if we think about the difference between what we talked about last week, extensive and intensive properties, heat, because it depends both on the temperature and on the mass. Remember, mass is an extensive property. So heat is also an extensive property. It depends on not just how hot the substance is, but how much of that substance you have. Temperature, on the other hand, is intensive. Right? It's only concerned with how fast the molecules in a sample of matter are moving, not with how many molecules there are. Right? Our scale for temperature is Celsius or degrees Kelvin. Notice that Celsius has a degree sign and Kelvin does not. The only difference between these two is where we define the zero temperature to be. We'll talk about that later. But we can directly measure temperature, of course, with a thermometer. So if you consider the question comparing a lit match and an ice sculpture. Now these are not to scale. The match would be much smaller than the ice sculpture. If you think about the question, which of these has a higher temperature, of course you would pretty quickly conclude it's the match. You know, if you touch the match, it's going to burn your hand, whereas you touch this ice sculpture and it's not going to hurt you at all, right, unless it's too cold. But the question, what has more heat energy? Okay, you may be tempted to say that the match has more heat energy because it's at a higher temperature, but remember, heat energy is an extensive property. So it doesn't just depend on how fast the molecules are moving. Obviously, they're moving faster in the lit match than they are in the ice sculpture, but there are like thousands of times more molecules of water in the ice sculpture than there are molecules in the match. So even though they're moving a lot slower, if you add up all of their motion, all of the energy that they have, that's still going to come out to be a lot more energy than the relatively small number of molecules that are zooming around quickly near where the match is lit. So the correct answer is the ice sculpture has more thermal or heat energy than the match does. All right, this is simply a slide to remind you that energy cannot be created or destroyed, but it can be transformed. So the total amount of energy in any system that we're studying is going to be fixed. It's going to be a constant number. So all that can happen with energy is it can simply switch from one type of energy to another type of energy. All right, and we saw that with our baggy lab that we did last week. Okay. So, heat and physical changes. All right, well, if we add or remove heat, basically we can do one of two things. All right, when I add or remove heat to a substance, I can either change the kinetic energy of the substance, which is going to change the temperature. This is basically either speeding up the molecules if I add heat or slowing the molecules down if I remove heat. All right, so that's just going to cause a change in the thermometer reading, right, which is based on the speed of the molecules. But also, in certain cases, when I add or remove heat from a substance, I could change another type of energy, which is called potential energy of the substance. And if I do that, I'm actually changing the phase of matter that is present. So remember our phases of matter: solid, liquid, and gas. So for example, if I remove heat from a liquid substance and I get it cold enough, eventually it'll freeze, right? Like what you did with your lauric acid yesterday. And if I freeze it, then I'm actually changing. I'm not changing the temperature of the substance at that moment that it freezes. I'm changing the potential energy that is present. I'm removing or lowering the potential energy in the substance as it freezes. So this is just a reminder of your phase changes. Really, we should have already written these down previously in your notes, which would have been at the top of page 5. So I'll just leave this up here for a moment. You can pause the video if you have not yet written these down. It's a good idea to color code your endothermic processes. Remember, for endothermic, you are adding energy to your substance, all right? And also the entropy is increasing. It's becoming more random or chaotic. The particles are spreading out and zooming around more randomly for your red phase changes. For your blue phase changes, they're going to be exothermic. The energy of the system is going to be dropping, all right? And the entropy is decreasing. The system's becoming more orderly or organized. So if I take my liquid, and I freeze it to a solid, I'm slowing the molecules of that liquid down, and they're becoming more tightly packed together and more organized. So that would be an exothermic process because energy is leaving my liquid. All right, but again, just make sure you have these before you move on to the next part of our presentation today. Okay. This diagram here is just illustrating the same thing that we talked about on the previous slide. We're basically just rank ordering our 3 states of matter by energy, entropy, and order. Entropy and order really are just synonyms, so these are pretty much the exact same thing. Entropy is the measure of disorder. So your highest energy state, of course, is going to be gas because the particles are zooming around everywhere. Your lowest energy state is going to be your solids because they're just vibrating about a tiny bit. Okay. Entropy is how chaotic a system is. And so we can clearly see that the gas state of matter is the most chaotic. The particles are spread out the furthest. And if we could see them moving, they'd be zooming around the fastest. That's also kind of related to entropy. Okay. As my gas condenses to a liquid, particles are becoming more organized. They're closer together, moving a bit slower. So my entropy is going down between gas and liquid, and it goes down even more between liquid and solid. This is clearly the most organized of the 3 states of matter, so it has the least entropy, and it is the most ordered or most organized of the 3. So if I'm moving from left to right, that is going to be an exothermic process because clearly energy is leaving the system as my particles slow down. Okay? If I were to move the opposite from my solid to liquid to gas, that would be endothermic. Energy would have to be entering the system to speed the particles up and move them further apart. Okay. So again, thermal energy can either be converted into potential energy, which is stored energy in a chemical structure, or it can be converted to kinetic energy, which is energy the object has because of its motion, its speed. More speed, more kinetic energy. All right. The last part that we are going to look at today is the heating curve, which is at the bottom of page 9. And if I can emphasize anything on this lesson today, it's going to be make sure you really have a good study and understanding of everything on this heating curve. There's a lot here. This does relate to what you did on your lab yesterday, and we'll talk about in class how this data on your lab sort of relates to this graph here. But if I look at first my axis, all right, I have time in minutes on my x-axis and temperature in degrees Celsius on my y-axis. So I can see that at the beginning, this is a heating curve. So at the beginning, my substance is at a very low temperature, right? And that's right at time 0. So it's at a low temperature. That's part A of the graph. And what's happening with this substance, by the way, is we're just exposing it to a constant amount of heat. So you can think of, like, for example, a big block of ice that's put into a pot on a stove. And if I had a thermometer that was sitting down in that block of ice, then it would be able to record these temperatures for me. So at first, as the stove heats up, the ice, let's say it starts out way below freezing. So first, all it's going to do is the particles are going to start speeding up, vibrating a little bit faster, and as they do that, the temperature goes up. Well, at some point, the temperature is actually going to stop rising. Now, I'm still adding heat to my substance, but I'm no longer increasing the kinetic energy of that substance, of that solid. I'm increasing the potential energy. What I'm basically doing is I'm freeing those solid particles, those solid atoms. Remember, they were like real crowded and crammed against their neighbor. Now they're starting to spread out and flow a little bit past each other, and that's called melting, right? So notice that phase change for melting on our temperature versus time graph, the slope is a flat line. The temperature is not increasing while the substance is melting. B would be the beginning of melting when you have all solid and you first start to see a little bit of it convert to liquid. All right. C would be when the last little piece of solid has melted. So it does take some time between B and C, depending on how much ice you have, for the whole thing to melt. But until the whole thing is melted, as long as it's well mixed together, the temperature really doesn't rise. Okay? Once all of your ice is melted, you finish converting all of your thermal energy into potential energy, then you have 100% liquid present. And if you continue to heat it after that, the temperature will just start rising again in a straight line. So it'll continue to rise here until it reaches a second temperature for a phase transition, which would be the boiling point. All right? And at that point, we didn't see that yesterday with lauric acid, because lauric acid is dangerous to boil. But if we had done that, you would have seen that the thermometer would indeed stop rising at some point. And when that occurs, your substance is going to start converting from liquid to gas, vaporization. That is going to continue, and the temperature is going to stay at the boiling point until all of your liquid has converted into gas or vapor. All right, temperature will not rise until the last little bit of your liquid has converted to gas. Now, if it was a closed container and you could actually leave the thermometer in there and measure the temperature of the gas, or if it was water, we call it steam, then eventually that steam would get hotter as it continues to be exposed to the heat source. And it would just continue to go up in a straight line as long as it was heated. Okay, but the key takeaways from this heating curve, the sloped parts of the curve are when you have only one state of matter present, solid for the bottom, liquid for the middle, and gas for the top part. That is the sloped parts of the heating curve. For the flat parts of the heating curve, that's where you have a mix or a blend of two states of matter present, and there's a transition occurring. For a heating curve, this transition is melting, and the second higher transition is vaporizing. Okay? And you can infer or determine your temperature for your heating curve. All right, your melting point is going to be, if you basically just take that flat part, if you extend it over to the y-axis and look at whatever temperature is there, assuming you actually have temperatures written over here on your lab, you can figure out what temperature the melting point was for your substance. All right, for the boiling point, you can do the same thing. If you have a heating curve, you look at where the flat portion is for the vaporization transition, and then just extend that flat part over with a ruler, or pencil, or a straight edge until you come across the y-axis, and then simply figure out what number you estimate what number the temperature occurred, or when your substance converted to boiling, right? And that's going to be your boiling point temperature. Okay. So again, make sure you study this graph. You know it well. I can promise you it's going to be on the quiz and on the test in this unit. So good luck studying that. All right, homework is going to be on page 10 of your packet, and I will check that tomorrow on Wednesday. So that concludes the lesson, and make sure you get your homework done. See you next time.